Hi, hello, hello. Am I audible? I think we can start. If you can hear me properly, then that's good. Okay, so in this session, we will briefly discuss about differential amplifiers, why they are used, and how does it operate. We had studied current mirror in the previous session, and these current mirrors will be used in one second. Differential amplifiers. All right. So first, let's say differential amplifiers are usually used in op amps, right? You must have heard what is an op amp. It's an operational amplifier. Use the output That's the amplified output as the difference of the input voltage. So let's say this is a block, this is A input, this is B input, and you get some, let's say this is V1 and this is V2, and this is a gain of A, you will get output as A times V1 minus V2. Okay, this is called as a difference amplifier. Alright, so ideally for an op amp, input the impedance looking into these input ports. What did I say? In the difference amplifier or an op amp, the impedance looking at the inputs should be ideally infinite, right? So like we have in the MOSFETs, for the voltage amplifiers, the input impedance should be as high as possible and ideally it should be infinite. Okay, now as I said, it uses a difference amplifier use an amplified output of difference of inputs. Okay, let's say I have this MOSFET, this is R out, so let's say this is RD, and this is V1 voltage, and this is V2 voltage. Okay, can you tell me what is V out? Usually, you must have seen the cases like this. This is V, let's say 1, and this is grounded. And simply, if I tell you what is V out, you will easily say this is minus GM times V1, right? Not GM exactly, it should be multiplied by this R and RD. Okay, so this is what your answer will be. But what if there is a voltage V2 here as well? And at that time, your V out will come out to be minus GM times RD multiplied by V1 minus V2. Here, second terminal is grounded, right? So this gives us the output as gain times V1 minus V2. So this is a difference amplifier as well. But why don't we use it? Okay, you will see in the next 2-3 slides, you will see that this is not what we use in difference as a difference amplifier. Right? Because there are some issues. So we know that voltage sources have intrinsic series resistances, right? So now we can write the circuit as V1, this is R1, RD, this is R2, this is V2. So this is how your circuit will look like. Now if I want to calculate this V out, or what is this I out, so let's say I short, because you know that superposition principle, you can ground or short the one and you calculate the response due to other source. This is how superposition works, and then at last you have to add them to get the total response. Calculate response due to V1. All right. So if I have to calculate current due to V1, I will make a circuit here, equivalent circuit. This is my V1, this is R2, and now this is grounded, this is R1, this is GM times V1, VGS, let's say this is VGS, GM times VGS, and this is my I out. Okay, it's called ground. So you will see that I out is GM VGS, and you can write I out as GM. This is at potential of V1, this is at V1 minus, but your S is also at potential I out times R2, right? So you will get I out plus GM R2 I out is equivalent to GM V1. So we give you I out as GM V1 greater 1 for GM. Similarly, you can calculate current due to V2. Again, we have to ground the first source. This is R2, this is V2. Again, this is positive, negative, VGS. This will be GM VGS, and this is I out. So if I calculate KCL here at this node, so I have I out, or not KCL, I can directly write I out as GM VGS. So my I out is GM VG. Now this is at 0 volt. So this will be 0 minus Vs, and this will be GM times 0 minus Vs is I out R2 minus V2, right? So my I out is plus GM I out R2 is equivalent to minus GM V2. So I out is basically minus GM V2 divided by 1 plus GM R2, right? So this was I out due to V2, and we calculated this I out due to V1. This is I out V2, V2. So now total I out is Let's call them I out 1 plus I out 2. 1, this is 1, this is 2. So my output total is equivalent to Gm divided by 1 plus GMR2 V1 minus Gm divided by 1 plus GMR2 V2, that is Gm divided by 1 plus GMR2 V1 minus V2. So you see that this fraction, let's call this alpha, I output total is equivalent to alpha with the V1 minus V2. So this is very less. This value is less, right? This proportionality factor is less, is not high enough. And also, you saw that there is a current flowing through the source branch. So that branch is loaded. So why don't we use this now as a difference amplifiers? One of the input is loaded. Loaded means the current is flowing through that branch. And second is sources, okay? And the proportional factor is not high enough. So what we use is, that is an alternative. We use the circuit which you may be somewhat familiar with. That's like this. Let me draw it. Okay, this is the circuit which we use. Okay, and here we intend to get infinite impedance, and thus we use a constant current source. Let's call it I naught. Okay, so at one condition, there will be equal currents flowing through both the branches. And when the currents are equal, then in one branch, there will be I naught by 2 and another will be I naught by 2 as well. And total has to be I naught because here current source I naught is connected, right? Now, incremental analysis. If we look at incremental analysis, if V1 increases, I know that V1 and V2 are such that they have opposite phases but are equal in magnitude. So if V1 increases, V2 decreases by same amount. So this means, and one second, this is ID1 current flowing here. This is ID2 current flowing here. So when V1 is exactly equivalent to V2, that means ID1 is equivalent to ID2 is equivalent to I0 by 2. So now if V1 increases, V2 decreases, that means ID1 is some current I2 plus some incremental current I. Similarly, ID2 is some current I0 by 2 minus I. So this you need to see clearly. So if V1 increases and V2 decreases, the current flowing through this branch plus the current flowing through this branch has to be totally equivalent to I0. So now if V1 increases, this current is I0 plus I, and so that means this has to be I0, this has to be I0 minus I. So only in that case, your total current is I0 here, alright. So this is the case. And now what do we want actually? We want here you have RL. We want this incremental current to flow through here, right? So that is the idea. So now in this case, first let's analyze the circuit. So this is the circuit. This is the circuit. So this is the current, incremental current I1. This is the incremental current I2. Let's call this M1. Let's call it M2. And suppose we are using the V1 at first. V2 is grounded. As I said, this is a superposition principle. We can use this. So if I connect it in this way, do you know we have studied, this is a source, right? This is source here. Now I have to analyze this circuit only, M1. But there is some resistance connected here because when you look at any inputs, let be it source, let it be drain and gate, you will find some resistance and then it is grounded. So can you tell me what will be this resistance? You are looking at R is impedance, looking at source of M2, right? So you know that if you look at source of M2, source of any transistor, you will get a resistance of 1 by GM, right? So let's call it as 1 by GM. Let's say that transistor is identical, so their GM will be equivalent. So now you have to calculate I. What is the current flowing through this circuit? Okay, 1 second. This is your equivalent circuit. This is, I hope this is now easy for you guys. This is your 1 by GM source, and this is GM VGS. This is R naught. We are calculating total R out here, right? R out here. So I connect a source Vx, and we have Ix as test source to calculate the R out, which I have clearly mentioned in the previous sessions how to calculate. So that it is the same. So KCL, if I do the KCL here, so it will be Ix equivalent to Vx minus, let's call this Vs here, by R naught plus GMVGS. I hope it's clear. If not, please stop me if anything is not clear. So it will be Vx by R naught minus Vs 1 by R naught plus Gm. So that is Vx by R naught minus Vs 1 plus Gm R naught by R naught. Alright, now Vs is the voltage drop across this transistor. So know that if Ix comes in this branch, it has to leave this branch as well. So your Vs will be simply Ix by Gm. So Ix is Vx by R naught minus Ix by Gm 1 plus Gm R naught divided by R naught. So if I suppose this Gm R naught is always very greater than 1, so I can simplify this. Ix is equivalent to Vx by R naught minus Ix by Gm R naught, and in the numerator as well it is Gm R naught. This and this will go. So your Ix is simply equivalent to Vx by R naught minus Ix. So it will be 2 times Ix is equivalent to Vx by R naught. So this means Vx by Ix is 2 R naught. Okay, so this is what you get, and this is equivalent to 2 R naught, R output. And similarly, in the previous discussion, we calculated this as okay, 1 second. I didn't do it. Give me a second. Yes, here. Mm, okay, we didn't do it yet. So now we found I R naught. Now we need to find effective GMR, what we call it as short circuit current. So we had this circuit. We had calculated that this is 1 by GM. Now we need to calculate this current, right? I1. Okay. This is V1. So you know, okay, let's draw the equivalent circuit. This is GMVGS, alright, and your V output is shorted. So this is ground. Let's suppose this is your R0 here. Okay, so simply your I is GMVGS. Let's call it I1, current due to V1. So this will be GM times VG is V1 minus VS. VS is R0 parallel 1 by GM. This is the resistance here. So this will be R is equal to R0 by GM divided by 1 plus R0. Sorry, R0 plus 1 by GM. So this is basically R0 by GM R0 plus 1. So this is GM R0 is greater than 1. This implies R is R0 by GM R0. R0 will go. This is simply 1 by GM. So Vs will be simply I1 by GM. So this is I1 plus GM times I1 by GM is equivalent to GM V1. So this is GM will go, but I1 is simply GM V1 by 2. Similarly, I2 will be GM V2 by 2. Now see that this is how your transistors are connected. V1, V2, incremental current here, incremental current here. So total current will be I1 minus I2, right? So this is I1 minus I2. So your I total will be GM by 2, V1 minus GM by 2, V2. So this is GM by 2, V1 minus V2. So this is your I total for the circuit, and your I out R out is 2R0. So therefore your output voltage will be simply equivalent to GM by 2 times 2R0 V1 minus V2. 2 and 2 will go. This is GM R0 V1 minus V2. Right? So this is what you get from this circuit. So you can make an equivalent circuit for it. So this will be simply GM by 2 V1 minus V2, and your total output resistance is R0, and then you can connect some output resistance, a load resistance Rm. So this is how you represent this difference amplifier. Okay. So now again, you saw this. If I connect now, continuing on this circuit analysis with different topologies. So this is your I0. This is V2. This is V1. If I connect some source here, I0 by 2. So this is I0 by 2. So when there is some difference, so let's call this R load. second. I know. Okay. So how we can study in this way as well. So this is I naught. If V1 increases, V2 decreases, so there will be an current of I naught by 2 plus 1. So there, below this node, there will be a current of I naught by 2 minus 1. Because then only the current through this branch will be I naught, right? So now here, you see here, there is I naught by 2. So what is the direction for the rest of the current? Here, right? So this will be I. And this I we calculated is simply Gm by 2 V1 minus V2. Now see here there is Gm by 2. Now if we want to increase this, so what is the next circuit we can draw? 1 second. The next circuit comes to our mind is we use 2 more transistors connected in this way. Okay, so this is V2. Now see here, this is your RL, this is your short circuit current. So see here, first initially I naught by 2, I naught by 2, right? So now if V1 increases and V2 decreases, so this will be plus I, this will be minus I, but at the same time, so this is like this. Here again, it will be again I naught by 2 plus I, right? Because in the same branch, there cannot be different currents flowing. So in this transistor again, there will be I naught by 2 plus 1 plus I. And now it is mirror here, current mirror. So now is the use of current mirror here. So here is the current mirror. So there is a current of I naught by 2 plus 1 flowing here. So in this branch as well, there will be current of I naught by 2 plus I. The condition is the transistor should be identical. Now come here at this point. There is a current of I naught by 2 plus 1 I coming here and leaving is I naught by 2 plus minus I. So the difference in the current is flowing through this branch. So your ISC is simply I plus I, that is 2I. So your short circuit current is 2 times I. So this will give you Gm times V1 minus V2. So you see that there is a increase in gain. Okay. So this is one thing we had to discuss before going to the questions. And now we will further see. Okay, how you can represent it? It is simple. You have this short circuit current of Gm V1 minus V2. So now we need to see what is this R right here. What is this R? In the previous part, for this case, it has simple 2 times R naught and Gm by 2 V1 minus V2. Okay, now we will see for this circuit. This may get pretty little bit complex. Please, if you have any doubts along the way, do stop me. Okay. First, I will draw the circuit for which we have to do the analysis. Okay, so this is our circuit. We have to do small signal analysis, so this will be grounded. This is open. So this is for the smooth flow. Okay. Now your V output is, we have to check this branch because V output will be connected to somewhere here. So what we need to calculate is R out, right? Because short circuit current we calculated, that is GM V1 minus V2. Now what remains is R out, right? So what is the procedure? Connected test source Vx, is that current of Ix flows through it, and this Ix will go in these two directions, right? Okay, clear? So now see that V2 is grounded for calculation of R out, and when you have to calculate R out, you have to ground the other sources. So I have grounded them. So now to see here that the current of I1 is flowing through this branch and it reaches here. So now we need to calculate what is this potential. Yeah, because there will be some potential because there is some resistance here. So we need to see what is this resistance. So we know that if we look at the drain of the sum terminal, sorry, this is, once again, this is source, this is drain, but this is a diode connected load, so we can calculate, its resistance. It comes out to be, do you want me to calculate or you know? Okay, let's calculate. So this is gate, this is source, grounded. This is RDS. This is drain, this is gate, and this is GM. One second. VSG, the direction will be upwards. Sorry. Okay, so now we have to connect test source here. So we'll see that this Ix I'm assuming that you now know what I'm doing here. VSG is equivalent to Vx by Rds. Okay. So this is Ix plus Gm. Vs is 0 and Vg is Vx. So this is minus Vx. So my Ix is Gm plus 1 by Rds times Vx. So again, so Vx, I will just first simplify it. This is Gm Rds plus 1 divided by Rds times Vx. Alright, let's see. So Ix will be Gm Rds plus 1 by Rds times Vx, assuming that Gm Rds is greater than 1. So this will be Ix is equal to Gm Rds by, so this means Vx by Ix is 1 by Gm. So if we look here at this point, so this is a resistance of 1 by Gm. So if it is a resistance of 1 by Gm, what is the potential developed here? Current of I1 is coming and there is a resistance 1 by Gm, so potential will be I1 by Gm, right? So the potential of I1 by Gm gets developed here, right? So now what is this connected to? This is connected to here. So this will be I1 by Gm. Let's call it Gm. Let's call it M3. This is M1. This is M2, and this is M4. Let's call it GM3. Okay. So this is I1 by GM3. So now for the transistor M4. Transistor M4 has a gate bias of I1 by GM3 now. Alright. So this is its gate. This is drain. This is source. And the source is grounded. Sorry. Okay. So this has a potential of I1 by GM3. So let's call this I2 dash. And I2 dash here is GM4 times I1 by GM3. And if GM3 is equivalent to GM4, this means I2 dash is I1. So now remember here, this is total current is I2 here. So if a current of I2 is coming here, so your I2 will be equivalent to I2 dash plus and a potential of here Vx is connected here, right? This is a potential of Vx. So this is Vx times this RDS, right? RDS 4. So this is total current. Or I can write I2 is simply I1 because I2 dash is I1. Vx times RDS 4. Assuming the transistors are identical, RDS 4 is equivalent to RDS 8. Now we have calculated I2. Now the next step is calculate I1. Alright. So this is your circuit through which the I1 can flow. Right. This has a resistance of RDS2. This has its own resistance of RDS1. And this one known as 1 by G3. Okay. So if you see that we have done this, you want to find resistance here, looking into this terminal, right? So you see, what is this own resistance looking at the source? That is 1 by Gm. Then you add it to the resistance. That will act as its. So this is a resistance source here, and then you will see, you will connect it to the resistance of 1 by Gm3, and then you can calculate the total resistance. I will just you can do it on your own. You have done a lot of it's called R out dash. lot of calculations in the previous sessions as well. I think you should be able to do this. And its approximate value comes out to be GM1. Okay. So now, if this is GM1, 1 by GM1, so my circuit becomes like this, a very simple one. Alright, so this is my I1. Okay. Now, if I have to calculate here the total resistance, you know that if this RT, if this is RT here looking into the drain terminal, it will be simply its own resistance plus what is the source resistance, that is 1 by GM 1 plus what it is gain, that is transistor 2 RDS, right? This is its gain. So this is RT is equivalent to RDS1 plus 1 by GM1 plus GM2 by GM1 times RDS2. Now assuming again that M1 and M2 are identical, that means RDS1 is equivalent to RDS2 and GM1 is equivalent to GM2. So your RT is equivalent to RDS1 . One second. Okay. Plus 1 by GM plus RDS1. So I can write approximately as 2 times RDS1 because RDS1 is very greater than 1 by GM. So this is the one thing. So if RT is this, so what will be here if this is IX and this is VX and IX here is I1. So what will be the potential here total? Vx will be simply current times total resistance, right? Or I can write I1 as Vx divided by 2 times RD, so on. So now we have I1, substituting it into I2, which we calculated here. So one second. So my I2 is, I'm repeating the expression, that is Vx times RDS3. So I2, now substituting the value of I1, that is Vx times RDS1, sorry, Vx divided by RDS3. Here it is wrong here. Okay, so this is correct one, RDS4. So this is Vx by 2 RDS1 plus Vx divided by RDS4. So this is I2 equivalent to Vx divided by 1 by 2 RDS1 plus 1 by RDS4. Now what is I test? Sorry, not that. What is Ix? That is I1 plus I2, right? Simple. Go back to the circuit. Here Ix is I2 plus I1, right? So I need to add them again to get the total Ix. I1 is Vx by 2 RDS1 plus I2 is Vx times 1 by 2 RDS1 plus 1 by RDS4. So Ix is, you see, this is 1 by 2, 1 by 2. 2 times 1 by 2, that is 1. So this will be Vx times 1 by RDS1 plus 1 by RDS4. So Vx, Ix is Vx times 1 by RDS1 plus 1 by RDS4. So R out is actually Vx by Ix, and that is equal to RDS1 parallel to RDS4. Or actually RDS3, we substituted it equivalent to RDS4. So R out is RDS1 parallel to RDS4. So whenever you get a circuit like this, whenever you get a circuit like this, and if this is M1, M2, M3, M4, your ISC, that is your short circuit current here, is GM times V1, this is V2, V1 minus V2, and your R out is simply the parallel combination of 1/2. You can write it as RDS1 parallel to RDS3. Okay, you don't need to calculate from the starting again and again. You can just see what is in 1/2 for that transistor and solve it. So equivalent circuit, simply this is GM V1 minus V2, and in this is not an equivalent circuit, and this will be RDS1 parallel RDS2, RDS3. All right. So this was about it. Let me check if there is anything else. Yes. Okay. So now coming to this part, coming to the circuit analysis, there are two types of gain now. Two types of gain. Till now we have seen only the differential gain. Two types of gains. One is differential gain, and another is common mode gain. And then there is one more term, that is CMRR, that is equivalent to, let's call it ADM, differential mode. This is ACM, so that is ADM. The goal is to have large value of CMRR. Okay. Okay, now let's see. This is the one circuit. I will give you. I will just come. I have to. I will give you 5 minutes to check this question, and till then, please post your answers in the chat. Okay. Hello. So you have got the answer of 1.2. Okay, this is actually a wrong answer. You can try once more. It's You can try once more. Again, 2 minutes. Then I will solve this. Let me just note down the values what are given. VCM, that is given to us 1.7 volts. I naught is 3 milliamperes. RD is 0.633 kilo ohms, and threshold voltage is given. What is the minimum allowable supply voltage if the transistors must remain in saturation? And for the saturation, we have condition VDS should be greater than or equal to VGS minus VT. Using this condition, you have to calculate what is the value of VDD. Okay, so this is what you have to calculate. I think you have calculated VDS. You have to calculate what is the value of VDD. Try it once more, then let me know your answer. No, not zero point 0.5. You just give me the answer. Let's see. You told me for the minimum condition VDS earlier, it has to be minimum 1.2. Now, if VDD is 0.95, how can you achieve VDS of 1.2? Yes, because this is supply voltage. This has to be larger than 1.2. So this is wrong. 0.95 is not correct. It's a simple KVL. You have to check the drop across the resistor, and then that has to be equivalent to 1.2. Now calculate VDD. 2.15. Yes, now it's correct. Let me just solve it myself as well. What did you do? I naught is given to you, right? So in this branch, the current will be I naught by 2, and in this branch, the current will be I naught by 2, right? So VDS min, you got 1.2. So for VDD minimum, it has to be I naught by 2 into RD plus VDS minimum. So VDD minimum is 3 point, what is the current? 3 milliampere by 2 into RD that is 0.633 kilo ohm plus 1.2. So that comes out to be what would got So that is what that is a value similar to your value, that is 2.15. Okay, okay. So this is clear. Okay, now we have this question. Okay, so I hope you can now tell me directly. You can directly tell me now what will be gain. Okay, 1 second. What will be I out? Can you tell me what will be I out? We just did a detailed analysis of the circuit to calculate I out. That is the short circuit analysis we did earlier. It is same. Okay, first let's say the first question. What is the first question? What is the GM? ID is K times VGS minus VT whole square 1 plus lambda VTS. Okay, so your GM is dID by dVGS. So that will be 2 times K VGS minus VT 1 plus lambda VTS. Alright, let's assume this term. Well, usually what we do whenever we calculate GM, we calculate at low values of VD. So we'll see lambda is given, and since here VDS is not given, so we'll ignore this term and we will say that GM is there something else that is given? Yes, I naught is given. So okay, we don't need to ignore anything. This we can translate into this formula 2 times K current, right? So and you can see that the current flowing in the one branch is I naught by 2, right? And I naught is given, that is 313 microamperes. So your GM will be, and K is also given 4.34 milli. I naught is 313 micro by 2, right? So you solve this, that is a simple square root. It comes out to be 1649.2 microsieverts. Okay?
May I ask you something, sir?
Yeah, please.
This 1 plus lambda by VDS, you are not considered
No,
in
no,
GM calculation?
yes, I have considered it, but since I don't know what is the value of VDS, what is the next way? Next way is to calculate from the current formula. That is this one, right? I hope you remember this formula, or you can derive this
I,
formula. Okay?
yes, I do, but lambda is not considered. I mean, my point is, since it is there in the equation,
No, no.
we are not. We can omit it. I mean, we can neglect it or ignore it.
1 second. Since okay, if you use this formula, you don't know anything about VGS also, right? So we
Yes.
cannot use this. The idea of this question is to use this one, this formula. Can you see the screen? Okay. So this formula says the GM, you know there are multiple formulas for GM, right? So this is
Yeah,
one formula which involves square root of K times what is the current flowing through the transistor, right? So the
yeah,
current flowing through the transistor is ID. Okay.
yeah,
So in this transistor as well, current is ID. And at this node, you will see this ID and this ID. It has to be total has to be equivalent to this ID1, ID2. Total has to be equivalent to I naught.
I know.
Okay.
Yeah,
Okay.
yeah,
So in the DC conditions, we assume here that the two half have similar current flowing through it because it's the current mirror, right?
yeah,
It is a current mirror. So at that condition, the current of I naught by 2 flows through here and the current of I naught by 2 flows through here. So that's why we don't need to ignore anything. We can directly use this formula and substitute at ID is equivalent to I naught by 2 and to get your GM.
okay.
Okay. So this was for GM calculation. Similarly, you can take. Can you tell me what is R naught?
1 upon lambda ID.
Okay, 1 upon lambda ID. Again, we can use directly ID value, that is 1 divided by lambda times I naught by 2. So this will be
Yeah,
2 by lambda I naught. So you can use this formula to
yeah.
calculate R naught. Now the third question is, that is the main question here, to calculate differential gain. What is the differential gain here for the circuit? We did the detailed analysis today for an hour. Can you now, because I chose the same circuit for the analysis and did draw the Norton equivalent circuit at last as well. So you can tell me directly what was the short circuit current we achieved. Here, let me just go back. Here, let's say this is R out, and this was the short circuit, this was the equivalent circuit, right? So from the circuit, if I call this as M1, M2, M3, M4, so you can directly tell me that ISC is,
GM.
right, Vn plus is this one, Vn minus is this one, and similarly R out is RDS1 parallel RDS2, okay, but here it's assumed that RDS1, I think, okay, lambda for PMOS is also zero point 0.2 and lambda for NMOS is also zero point 0.2. So that means their RDS is equal, right?
Yeah,
So RDS1 is equivalent to RDS2 is equivalent to R naught, that is 2 by lambda I naught. Okay, so your V output is GM times 2 by lambda I naught V plus minus V minus. So gain is simply 2 by lambda I naught GM. This is how we can directly calculate a gain. And if you want to do detailed analysis, then again what you have to do is ground one terminal and do the analysis using this Vn plus, calculate V out. Then ground this terminal, do the analysis using Vn1, Vn minus and calculate V out and then add them. Okay, so this is how you can, if, wait a second, if, let's see. Okay, so are there any questions related to we did some, there would have been some things that would have been complex as well. So
can
are
you go
there,
to earlier slides when you've done the calculation stuff?
yes, which one?
The you have done the detailed analysis of the circuit, drawing equivalent circuits. Yeah, these are the ones.
Mm-hmm.
Now, now the point. My point was RO is at output. which is
Yes.
parallel to GM-VGS, correct?
1 second. Let me see the circuit. This one?
Yeah, yeah. And this you have done the equivalent circuit. I mean, small signal analysis.
1 second. Let me go from the first slide.
Then first slide, go little down, sir.
Okay. 1 second. Where I have used four transistors or two transistors?
We are talking about the analysis, what you have done at the output. We are short.
This
Yeah,
one.
here we can go.
Hmm.
Now,
In this one?
just a minute, I missed the point. Can you go to earlier slides?
Earlier, okay.
Just a minute, just a minute. Earlier than that, I missed out the slide.
Okay,
Yeah,
I will go.
this is the one I'm talking about.
Okay.
Now, you have GM-VGS,
Hmm.
correct? And that's a current going over there.
Mm-hmm. Yes.
And then you have made it parallel to RO, parallel to 1 upon GM. That is
Okay.
something I have not followed, sir.
Okay. Okay. Actually, mhm. 1 second. This is uh, this is for PMOS. 1 second. Mm,
Yeah,
This is
this is the one you should have started with.
okay. This is okay.
This, yeah,
This is okay.
the
So
equivalent circuit is okay. For this point is okay. Then,
okay. 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 1 second. Mm, This is one. Okay. This is the one we are talking about here.
GM and RO are parallel to each other, correct, sir?
Yeah, I got your point. What you are saying.
And then 1 upon GM is in series with both of them, if I'm rightly getting. Otherwise, correct me, sir.
You are correct. GM, 1 by GM is in series. That is a source
It's a series
regeneration.
to a parallel combination of GM and RO, correct? If I'm
G,
rightly getting, if I may be wrong, please correct me.
GM and R. Okay, 1 second. I will tell you why I have written it in this way. 1 second. This R node, right?
Yeah,
This R node is actually. 1 second. I got your point. This may lead to confusion.
many times in the circuits also, sir, I found that I am going wrong. Primarily
Mm-hmm.
because I tried to calculate on the GM parallel to RO
Mm,
or
Okay.
RDS,
So,
and
so
then
this
subsequently output
this
side.
this
Sorry.
is this is actually like this. This is clear. This is 1 by
Yeah,
GM.
yeah,
This is GMVGS. This is
yes,
clear as well. And
yes.
this is R not here, right?
Yeah, that's right. That's right.
That's right. Okay. So this is I1 coming here.
Yeah,
Since this is
yeah,
grounded,
correct.
this is grounded,
Yeah,
right? So this is I know I1 here. We have written I1 here. So this is grounded terminal. This is also grounded terminal. That's why I drew it here.
okay.
Okay. But I think you are correct. I should not have drawn it this way.
I mean, I may be wrong. Please correct
Yeah,
me.
no. I think you're correct. 1 second, because let me just recalculate the values. If I take, let's use new slide. 1 second. Yeah, right. So let's
Tell me one more thing, sir. This current is in negative, this one, no? It's a
Which
negative
one?
polarity.
Which one?
The current which is I1, which is flowing from the earth, I mean, from the short earthing terminal to the this one is so they are at the same potential. You are saying both are them are grounded either end.
No, 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 not both of them are grounded. No. So then there won't be any current, right?
Yeah. So that's another point which I want to drive, sir. The both the ends are grounded, correct?
No, only one end is grounded.
The top one is grounded, correct?
Oh, yes, yes, yes.
The down one is still having some potential.
Yes.
So if that be the case, it is a negative current, correct?
Negative current. By negative current, what do you mean by negative current?
I mean, the polarity is, polarity is negative. I mean, minus
One
sign.
second. Oh, okay, this is visible, right?
Yeah, yeah, very much, sir.
This is drain, this is source. So current will be from drain to
Drain to
source,
source.
right? So
Yes.
now if you want to do incremental analysis,
Yeah,
so we draw the circuit and this potential that was at some DC bias is grounded, right?
yeah,
Okay, but there may be increase and decrease in current, but the direction, it obviously the current direction depends on what is the waveform here now. But overall current, if you look at the overall current, total current will always flow from drain to source.
hmm,
It won't change direction,
yeah,
right? Because this is total current is I DC plus I AC.
it's a small signal one. Yeah,
Yeah, okay. So this DC is always from drain to source. So now what changes is if this was DC, on top of it there is some AC fluctuating in this way.
yeah,
Okay. So the total current direction is always from drain to source.
hmm,
Okay, now we were talking about this. So let's see. This is the circuit. Okay. So if I now, okay, I need to calculate R, right?
yeah.
R is why did I use GMR not? I need to check for what I have calculated it. Hmm, okay, M1 is GM GM by 2. This is actually this I have used. Can you see here? Uh, Here this R. Okay, so this is grounded, right?
Yeah, this is grounded. Yeah,
Okay, so to calculate R total here, what is the R total here? What will you do? You can directly see that this R1 by GM is parallel to R0, right? Because they have the same terminal and another terminal is grounded. Okay,
okay, okay.
okay, so they are 1 by GM parallel R0, right?
Yeah, but then, sir, you have to consider the other GM also, no, in the picture.
Okay, now when you calculate RT, V1 you have to ground, right? So when this is grounded, okay, when this is grounded,
Yeah,
I will connect a test source here. I will connect a test source here. Now this is 1 by GM, this is R0. If it's not clear, please do let me know. And this is GMVGS, right? And this is now
Hmm.
again grounded. Okay, this is clear.
Okay.
Okay, so now the current of IX flows here, and this is again grounded here. So if I use a KCL hat here at this node, so this will be IX plus GMVGS, okay,
Hmm.
and this will be 1 by GM parallel R naught is 1 by GM, right?
Okay.
This is a parallel combination using GM
Yeah.
R naught greater than, so I will use just this is equivalent to 1 by GM, so I can directly write current leaving as 1 Vx by,
Hmm.
sorry, not by, this is multiplied GM, right?
Yeah.
Okay, so now this is plus GM VGS. VGS is VG, that is 0, minus VS. VS is again Vx. So this will be GM. So this means this will be Ix minus GM Vx is equivalent to GM Vx. So your Ix is equivalent to 2 times GM Vx. So your Vx by Ix is 1 by 2 GM. Right?
Hmm.
So yes, I think this is something. 1 second, let me check.
Sir, if I calculate GM parallel to RO and then
Hmm.
in series with 1 upon GM, will it give the same answer?
GM parallel to R now?
GM, the top one answer, top one which you are talking about, the upper part of the series circuit. So
Mm-hmm.
equivalent circuit. If I calculate GM parallel to RO and they
1
are
by
in
GM.
series
1 by
with
GM parallel to
upon
R.
GM, is that give the same answer, sir?
1 by GM R out is parallel, right?
Because there 1 upon GM is the downside. I mean, what I'm saying is at the load side, also the ground side.
This one,
Will
this
it give
one.
the same answer?
I'm not actually getting your point. Which
The point I'm saying, sir, GM is GM on the top one. I mean, upper side
this
of
one,
the circuit.
this one,
Yeah,
this one.
the very
This
good
is
point. I mean, GM and RO. If I
this is this
basically
is
they are parallel to each other, if I
this is
calculate it that way, say GM into RO upon GM plus RO in series with 1 upon plus GM, will that give me the same sort of output impedance?
first thing. This is GMVGS. You are talking about this
Then
GMVGS.
GM is okay. GM is the current we're talking about. Correct, sir?
Okay, okay.
The GM is the resistance part of it, the conductance part of it. So if I consider 1 upon GM
So
plus
that
1 upon
1 upon you will only get 1 upon GM if there is some another component connected to it. So that's why here it is written 1 by GM. It's because we are looking at source of some other transistor.
yeah, that's right. Yeah.
Hmm. Okay, then go on. Wait a second. I think
Another about, sir, I want to ask you this VX, what you have connected, sir, the
hmm.
source. Can I connect on the other side? I mean, on the other side also you can connect on the grounding that
So,
part of it, or is it?
so this is actually a procedure. This is
Okay.
actually a procedure to calculate a resistance from a particular node. For example,
Okay.
if I want to calculate resistance looking into this node, right?
Yes.
So I connect
Yeah.
Vx Ix, then I have to just finally the resistance will be. Vx by Ix, right?
Okay, sir. Okay.
So you have to analyze your circuit in such a way to get it in the formulation of the form such that you can get Vx by Ix. So that is the
Okay.
idea.
Okay. Okay.
Okay. So 1 second. Mm, this is actually okay. You can just if you ignore this for a second. So this was clear, right? GM V1
Yeah.
by 2. This was
That
clear.
is clear because they have the same potential. Both the ends,
Hmm.
other ends are grounded. So
Okay.
that's
So
so you
that
can just
was
replace it. Yeah. You
so
can
that
just
was clear.
replace it now. Yeah,
So
that is clear. That is okay. That is
so
okay.
okay.
I didn't put it for in the first shot, but you were nicely explained with it. So that's okay. That's okay.
So okay. So this was I think just for calculating the total resistance here. Okay. So now we can. I have just shown this. I have to check again. Check again the values. Okay. So now, but you can see here. mm, You can see here I have written R out as 2 times R naught, right?
Yeah.
I have written R out as 2 times R naught and I must have calculated it somewhere, right? Here, this is already here calculated here.
Yeah.
Vx by Ix. If you just draw the equivalent circuit, this is clear, right?
Yeah.
1 by Gm R1.
Mm.
Actually, this we need actually. Okay.
Yeah.
So you must have followed this. This is a circuit. The first step was to calculate R out. So R out I have calculated by using the test source, and you will see that this comes out to be 2 times R naught. So that is the idea, right?
Yeah.
So that for that this is the final Norton equivalent circuit. Okay.
Mm.
So you get a current of Gm by 2 V1 minus V2 in parallel with 2 times R naught. Okay. So besides this, are there any further questions? We still have some time left. In the
Sir,
next,
is it? Sorry.
okay, go on.
Sir, is it possible that in the we can calculate the GM and RDS or GMB and does the parallel calculation and then derive it because some formulas are somehow doesn't match really. Somehow I may be going wrong somewhere, but even RDS one or say RO at RO they doesn't match. I mean, the formulas, what has been derived, I find it little complex because they doesn't final figure. The denominator matches, but numerator at times
Uh,
doesn't match.
Okay, so when you solve them, your answers don't match. That's what you are saying.
Yeah, and then a bit confusion. So
Okay, as I said earlier, so it boils down to the KCL and KVL, right? So
that's right.
you have the transistor, let's say.
Yeah. So another point we try to drive is calculation of the short circuit current
Mhm.
and output impedance. For the output impedance, we have to look it from the output side and then calculate and see the division of current and then subsequently find out the
Okay. hmm So this is your, let's say, small signal analysis. So
yeah,
this is your V out, right?
yeah,
And this is your RL.
yeah, this is the RL, yeah.
Okay. So when you find a short circuit analysis, when you have to do short circuit analysis,
Hmm.
you ground this directly. One.
Okay,
You ground this directly. Okay. Then connect. Then check what is the ISC.
okay,
Okay. So and if you draw any equivalent circuit. This is RS, this is GMVGS, this is R naught. Now, if you have to calculate R out, simply, let's say there was RL as well. If you want to complicate the situation, you will connect test source here. But to make it easy, connect a test source here such that this is Ix and find this R out, and then R total final will be simply R out parallel RL. Okay, this is how you simplify your analysis. Okay, similarly, you can connect here looking into the source. So this boils down to you have to follow the KCL properly. The node voltage between the two ends of the branch. What is the current flowing in going out? If you do that properly, then you will get the same answers.
Okay.
So is there any circuit you have that you didn't get a right answer?
There are few. Let me try again.
Okay. You can please let me know in the next session if
Yeah.
there are some issues. Okay, so I think we will continue with these differential amplifiers in next week as well.
Okay, sir. Okay.
Okay, if there is not anything else, then we can end the session.
Yeah.